And also in terms of improving in the course, I've noticed, and I need to get with Owen on this, that attendance has been an issue. Like today, there's something like 10 people missing, and that's not uncommon. So you basically, in order to not get failure for non-attendance, you get like, I think maybe 4. Your cushion is 4 misses throughout the whole semester. So if you that cushion is for things out of your control, like you're just glued to your bed because you're sick, or your transportation broke down, or something like that. So don't just choose not to come. That's going to be very detrimental to your success in the course. And also, then when you do have something that prevents you from coming, you'll have run out of your cushion. Okay, so if you're looking at 3 or 4 absences by now, that's way too many. That's way too many, and you really don't have room for any more. Okay, so in terms of success in the course, you've got to come to class. Okay, you've got to come to class. All right, and so I'll probably be asking Owen, who's got 3 or more absences, and be sending you an email to remind you. There's no room. So don't. If you can come and you're choosing not to, that's a very, very bad idea. Okay. So I want to. So this picture should look familiar. Why don't you get a partner and talk about, there's probably a dozen things to talk about in this picture. So get your mind oriented. Hopefully everything hasn't fallen out of your brain over the weekend, the long weekend. So get a partner and talk about the many, many aspects of what you're seeing in this picture. Go.
Yeah, well, that's like so let's say it's the second set, 4.2 seconds. That's the range. Stop. On the right side. On the left side. On the right side. Then like your dots on the right side. That just like shows you the bits and changes that are dots in those types of sentences or whatever delta y's that correspond to those.
So the y value on this graph, so I'm going to let you turn you loose for another 30 seconds. What does the y value on this graph represent, and how is this showing, in what way is this showing what that y value is? Okay, so what does that y value represent, and how does this thing right there, what is that showing about that y value? Go.
So y value is small.
So the last one at the top, like,
Okay, let's regroup and let's take a look. Okay, so what is this showing here? So what was your response? So what does that y value mean, and what does this blue line with dots on it relate to that y value? Go ahead.
Well, the y value would be the accumulation at any given point, and the dots.
And let me stop you there. At any given point, this y value right here?
Oh, that's at the final point.
Okay.
And the dots, it's kind of like how fast the rate's changing. Like the closer the dots are together, the faster the rate's changing at this point.
So the dots are closer together, the rate is higher.
Smaller.
So,
Oh yes.
okay. Who wants to say more? Adonijah.
When you take the y value on the rate graph and times that delta x, it's going to be the difference between one point to another. So like at the beginning, you have pretty high rates, so there's pretty big distances, and then as you get in between that like 2 and 3 distance on the left graph, those dots get closer together on the right graph.
Okay. So what are these distances? What do these distances represent? Yeah, all the changes, or how, like again, how do things accumulate? If this y value is the accumulation from where to where? Yeah, like it's from like 1 to 4.2. And how do things accumulate? And the bits are?
The dots.
Not the dots.
Well, the amount of accumulation.
Yeah, so our bits of accumulation are our delta y's, right? And those delta y's come from? This is showing that our delta y's come from? Delta y equals? K delta x, right? So with each constant rate of change, multiplied by the little bit of change in x, gives us the little bit of change in our quantity. And then add all those up from 1 to 4.2. This is showing add all those up from 1 to 4.2, and we get the accumulation up to that point, starting at 1. Okay, so there's an alternate way to look at this, and many of you, so not many, some of you have alluded to this over the last couple weeks. Connor just alluded to it earlier, okay, and so I gave him a hard time, but it's time to just mention this. Here's an alternate way to think about, so what was our integral? Our integral for this value right here would have been? So how could we write this situation as an integral? So I'll do that. You do the rest. What goes down here? 1, 4.2. Okay, since we have both values here, we can choose anything we want. So we can do r of x, it's fine, or r of t, doesn't matter. Okay? And that would be?
Accumulation 4.2.
Right, it'd be accumulation of 4.2. We could do minus a of 1, but a of 1 is 0, right? Because that's where we're starting. Okay, so another way to look at this integral here is that the rate for each of these rates is the y value. So the rate could be thought of as that, R1 could be thought of as that height right there. The y value is that distance. Agree? And what's delta x? It's this right here, right? So R1 delta x could be thought of as an area of this rectangle because the height of the rectangle is the rate and the width of the rectangle is delta x. Do you see that? So that little bit of delta y we could think of it as the shaded, so delta y1, as the shaded blue area. Do you see it? Similarly, the next little change in y, was it more or less? Smaller rate, so shorter rectangle, same delta x. So that area of that rectangle, base times height. Base times height. Okay, so that integration is remotely related to areas of rectangles is entirely an artifact of the fact that we're graphing in rectangular coordinates. Okay? It's just because our delta x happens to be horizontal width and our rates are height that it just turns out that these delta y's turn out to be areas. Okay? So it's not a deep mathematical principle. Okay? It's just kind of incidental. It's kind of a coincidence. Because if you graph in a different coordinate system, then it would no longer be area. If you graphed our little changes in y, say in polar coordinates, and you're familiar with that, then these changes in y would no longer be area. It's just because we're graphing in rectangular coordinates. Delta x is horizontal, rate is vertical, that it turns out that we get these areas. Okay, so what happens if we make delta x smaller? What happens to those rectangles? They're going to get thinner. And we know that the tops of those rectangles are like our step function, right? And those are matching the curve better. So with skinnier rectangles, the sum of the area, so the sum of the delta y's, or the sum of those rectangles, is getting closer and closer to this area under the curve. And so as delta x goes to dx, our integral equals the area bounded by the x-axis and the curve. Okay? This is pretty superficial. So we're experts at understanding that this is about quantities and rates of change, right? This is about quantity and rate of change. And this is just kind of, like we said, like an incidental result of the fact that we're in rectangular coordinates. So the area is superficial compared to the way we built it up in terms of rate of change and the quantity y, the accumulation of the quantity whose rate we had at the beginning. Okay, so I did want to point that out. Some of you had calculus before, and that's what's emphasized in a traditional calculus course, that integrals are about area. But you could know that and not know anything that we learned about rate of change and quantities and how these quantities change together. And that's universally what calculus is, the tools for helping us see how these quantities change together. The x quantity and then our focal quantity. Any questions on that? And so then at the end of the course, we're going to kind of come around full circle. And the end of the course, we'll explore some problems like this, where we deal with integrals as areas. Okay? But we need to kind of make the loop back around to get there. Okay? So now we're going to start the second half of the journey. That's last semester. But anyway, so we have been working on this whole first part of the course, getting accumulation from rates. And now we're going to be getting rate from accumulation. So given accumulation, an accumulation function, what's the corresponding rate function? So here's what we did. We started with exact rate of change, right? And what would we do from there? Step function, and what kind of function was the step function? Approximating rate of change, right? And we used left or right or mid to make a step function that approximated that rate of change. And from there, what did we build? Approximated accumulation, which was what kind of function?
Summation.
Piecewise linear. So is this a curve right here? No, it's a bunch of little line segments that we're getting from those constant rates, right? All pieced together. And from there? And what was the key from moving from approximate accumulation to exact accumulation? What was that? How did we get that? Yeah, and then very small, right? So taking those delta x's, making them very, very small, so small that it converges on this exact accumulation. So that's what we've done. So now what we're going to do, and then we saw that the integral notation, we could just go right from exact rate. So starting with r of x. We did all the hard work in between to understand what this notation meant, and since we've earned the right to just write down what the exact accumulation function is, because we saw the process to get there. Okay. So now we're going to take the reverse journey. Starting with an accumulation function, okay, we're going to go to, this is just backwards. So we're going to create an approximate accumulation function for the purpose of getting our approximate rate of change step function. And then from that rate of change step function, exact rate of change. And then once we do all that hard work in the middle, again, we'll have earned our privilege to, starting with an exact accumulation, go directly to exact rate of change. So the question is, where do exact accumulation functions come from? What is accumulation about? How is it different than rate? So where do exact accumulation functions come from? Any idea? What's that?
Position graphs.
Position graph? Okay.
Like it's like acceleration and velocity of position.
So if it's like distance or position. Any other ideas? So where do exact accumulation functions come from? What are they? They're really the types of functions you've been dealing with your whole career in math. Okay? They're just a quantity function, but now we're just going to kind of take a different perspective on it. Instead of seeing it as a quantity function, we're going to see it as an accumulation function. And so it goes back to what is accumulation? Things accumulate. A quantity accumulates how? Little bit at a time. Little bit at a time. Okay? So the area of a square. That function would be area is x squared. Okay? So if we let, what does x represent here? Side length, right? And so if we let the side length increase a little bit, what happens to the area? It increases a little bit, okay? And so we can think of this function as this quantity function that's just telling us what the area is as accumulation just by thinking of the side length increasing a little bit at a time. And so then what happens to the y value or the area? It has some corresponding little bits of increase to its from a 0 side length up to its whatever its current area is. Okay, So that means if this area function could be represented as an integral, right, of some rate. If this area is an accumulation function, then it could be represented as an integral of some rate. Okay, similarly like a sphere. Okay, the quantity could be the volume of a sphere. But we can think of it as the radius grows, little bits at a time, the volume increases, accumulates, and so it can be thought, that quantity function can be thought of as an accumulation function. And our goal then is to find what is the rate that's characterizing that accumulation. So any function that gives an exact amount of one quantity as a function of another is an exact accumulation function, and therefore can be represented as an integral of its exact rate of change function. We just don't know what that rate of change function is, and so this is the reverse journey that we're on. Given that we know how it accumulates or what the quantity is, what is the rate that defines how it accumulates? Okay, so what's another example of this? Say like so if X is the number of units produced and sold, and P was the profit for producing and selling that number of. So how can the profit be thought of as accumulation? So that's just a plain old quantity function. How can we see it as accumulation?
Every unit you sell, you get a small amount of profit.
Okay.
And you accumulate all those profits as X increases.
Yeah, and normally these functions look something like this. Okay? So, he said every time we make and sell more units, the profit goes up a little bit. Okay? How about miles traveled on the highway and gallons of gasoline? Gallons used. How can the gallons used on driving down the highway be thought of as an accumulation function? Yeah.
The more miles you drive, the more gas.
Yeah, so as you drive little bits of miles at a time, the gallons of gas that you use is going to go up. And depending on your speed, the rate which the gallons are burning is going to change, right? And so it's that. So here's our accumulation of gallons used. Our goal now is to find what is the rate function that characterizes that accumulation function. So going backwards now. Okay, so we'll start working on that Wednesday. There may or may not be homework. Look later tonight.
But I'm